my intention today to cover everything that you need to know for nuclear reactions in one lecture. I think I can do that, actually. I'll have you talking and thinking like a nuclear scientist by the end of this. Or at least I'll have you knowing what we talk and think like, and then you can go ahead and improvise later to kind of pick up your own practice. So the first thing to keep in mind is this weird notation that we use in nuclear physics. So unfortunately, I thought maybe I could get away with not doing this. But if we're going to ask you to look online at the National Nuclear Data Center and pull down information, you need to understand this notation. So this is how you might think of a nuclear reaction as being written out. Projectile plus target goes to something heavy coming out plus ejectiles, the lighter things coming out. This is sort of like what chemistry does, okay? But that's not what we do. What was noticed by folks really at the dawn of the nuclear age was that reactions where you have a certain light incoming particle and light outgoing particle, like a neutron in and a proton out, that all reactions of this sort had similar properties. Or you have a neutron go in and get stuck in the nucleus, and then have just gammas coming out of the nucleus be excited. Or probably the most important one for what we're going to discuss is a neutron coming in and fission happening. In other words, neutron-induced fission looks fairly similar for most nuclei that you would have it take place on, regardless of what the nucleus is. So uranium-233, uranium-235, plutonium-239. All of them had relatively similar behavior. So that's why this notation became popular, where you put it together inside of a parenthesis with a comma separating it. So the target sits on the outside, on one side. The heavy residual sits on the outside on the other side. The projectile, which for most of what we've talked about today, like a neutron, is the first thing inside of the parenthesis, and the ejectile is the second thing. So the target, the projectile, and the ejectile, and the residual can be massive, meaning a proton, a neutron, some sort of an element with some number of neutrons and protons, etc. Or it could be massless. It could be a gamma ray or an X-ray coming in. So for example, one whole class of reactions that we'll look at a lot in forensics is neutron capture, which then results in the emission of gamma rays. Because once you capture that neutron, you have all this extra energy, and it's got to get out. It'll get out in the form of gammas. Okay? We also can use a shorthand form, like F for fission. So when I say NF, I haven't told you, so there's some nucleus out here, X, and there's no reason for me to write something out here. Fission means it broke up. So I could write this out in detail and say I had a strontium-95 or something like that, and a barium 140 something. But you don't do that. With fission, you would just write it as NF. Okay? So there are 3 rules that you need to keep in mind about nuclear reactions with respect to this course and everything that we would cover here. Rule number 1, nuclei are really small. So the chance of one hitting another is tiny. I know that this sounds ridiculous stated in this way, but it really is important. You know, when you take 2 different chemical reactants and you put them in a test tube and you shake them up, you might die. But if you do that, right, reactions happen really quickly. And that's because actually atoms are pretty big. And the range of the interaction between them is infinite. Nuclei are really small, and until you get within that magical 5 or 6 Fermi, nothing happens. At least nothing nuclear. You can have something electromagnetic happening, but that's it. So the bottom line is, it's really hard to get a nuclear reaction to happen. And if you want to get two nuclear reactions to happen in a row, that's hard squared. 3 is hard cubed, okay? It becomes really unlikely. In general, we never plan experiments to do that. Weapons violate that rule. There are so many neutrons created in such a short time, in such a small volume, that you actually get multi-order reactions occurring. But really, within the same short period of time, that's about the only place where it happens. Okay? Oh, this is out of order. Let's do that, but that's fine. So we'll go to 3 first, but I'll jump back and forth. Fusion reactions require high energies, because when we talk about fusion, it's generally the fusion not of a neutron with something else, but it could be a proton or a deuteron or a triton merging with another proton or deuteron or triton within 6. Okay, these things have charge, and so they have to overcome a barrier. They require high energies. So number 2. And I know why this happened because I did reorder these. As neutrons slow down, their chances of hitting a nucleus increase. And their chance, I should say, that's weird. Okay? But it's true. It's not just that they zip past the field of the nucleus too fast for it to interact. No, that's not it. If you want to use that analogy in your head, you can, but it's a little dangerous. This is strange. I mean, at the end of the day, nuclear reactions are somewhat counterintuitive. And so rather than go into a great discourse about this, I'm just going to say you have to accept this, and we'll be specific about it. As a neutron slows down, its chances of interacting with the nucleus increase. And if you could ever stop a neutron, its chance of interacting with it, wherever it's stopped with respect to, in principle, becomes infinite. That's very strange, but that's the truth. And you'll see how that manifests itself as I go on. So let's first of all start with this rule number 1, that nuclei are really small, so the chance of one hitting another is tiny. Okay? So I'm talking about hitting things. Let's start with the target. Okay? I've got a big fat target, and I'm going to throw a nucleus at that target, right? No problem. I hit this thing. I can hit it again. It's a large target. It's easy to hit this thing. How easy? Well, it all depends on how big the target is. If I identify a radius with that target, the ease with which I can hit it, you'll notice my chance of hitting it just is proportional to its area. Not its volume, not just its radius, its area. And the area of a circle is pi r squared. Maybe I can add another thing here. Generally speaking, nuclei are circular in radius. Even the most deformed nuclei, which we know and see, like some of the actinides, like uranium and plutonium, if I drew a picture of one up here, and any of you had even a slight amount of astigmatism, you'd say it was a circle. It's a pretty small difference from sphericity. So smaller targets are harder to hit. Okay? I create particles, and now I can actually slip between them, right? It just gets harder. So in this picture, what I was trying to show was that the radius was a half of the previous radius. That actually, if I had 3 of these targets, it's still harder to hit. So what does this mean? It means that as I shrink the size of my targets down, you need a very large number of them to give you the same probability of hitting them. Okay? That's pretty straightforward, right? Is everyone with me up to this point? This doesn't even look like nuclear physics yet, right? Is this okay? You should stop me at any point. This isn't like going to be a magic trick. I'm not going to pull a rabbit out of my hat. When I do that, I'll warn you. I'll say a rabbit is about to appear, okay? So one way that I can increase my chances of hitting this thing is if I stack more of them in a row, okay? So instead of just having one row of smaller targets, let me get multiple rows of them, okay? If I have multiple rows, then I start shooting, I can miss a front target, but hit one of the back ones, right? Miss the front, hit a middle row one. In general, the more rows that I have, the easier it is to hit. Okay? So this is basically, if you want to cause nuclear reactions to happen, are you ready for it? You need a thick target. You need layer after layer after layer of target. This is actually what most of weapons design boils down to. You need to make things very compressed and very dense because the projectiles and their targets are really small and they easily slip past one another. Okay? It's important to just take a pause and think for a moment about the relative scales of these things. Okay? Roughly, how big is a nucleus? In terms of, you mean meters or centimeters? Anyone? Don't be scared. Come on. What?
Angstrom.
Angstrom for a nucleus. Who votes that angstrom is the size of the nucleus?
I'll see the angstrom and raise a Fermi.
You'll see the angstrom and raise it to a Fermi. I like that. Okay. I like that, and that's true. I think I would decrease it to a Fermi, but I agree with you. Yes. It's about a Fermi. A nucleus is about, it's actually closer to 10 Fermi than to 1. Depends on the moderate nucleus. But it's somewhere between 10 to the minus 14 and 10 to the minus 15 meters, kind of, if that's the radius that you think about. That's the nucleus. Now, how big is an atom? Angstrom. Very good. Atom is about 10 to the minus 9, 10 to the minus 10. Again, it depends on the size of the atom. Big atoms are, well, bigger. Okay? What does this really mean? It means that there's a factor of 100,000 difference between them. For all intents and purposes, your life right now is dominated by atoms. Your cells are made up of atoms. The density of matter in your body is relatively constant, and it's roughly at a value where each atom is touching. That's your density. We have to decrease the distance between your nuclei by a factor of 100,000 to get the nuclei to touch. If I decrease the distance between things by 100,000, how would the density go? So I've got two things, and I'm now going to decrease the distance between them by a factor of 10 to the 5. That's about what we have here. How would the density go?
Would mass increase?
It would increase, absolutely. How much would it increase? That's the normal and reasonable thing to say, by a factor of 10 to the 5. And that would work if we were in just one dimension. But we're actually in 3 dimensions. So if I decrease the distance between things in all dimensions by that much, it turns out the density goes way up. It goes up by 10 to the 5 cubed. So generally speaking, we are about 1 gram per cubic centimeter. The nucleus is about 10 to the 15 grams per cubic centimeter. That's the kind of density you need to get the nuclei on top of one another. So in other words, when I've been drawing these pictures, if I was to make this realistic, my pixels, if I had 1 pixel here, I have to have 10 to the 15 pixels between them. That's the density of matter in your body right now with respect to the nucleus. Nothing. It's a blank screen. There's nothing there. So nuclear reactions, really, you need many, many layers, right? If I have 1 little dot and then 10 to the 15 is a million billion. So a million billion little dots out to the next one, that's nothing. It's empty. We're basically empty, okay? Which is not a philosophical statement and not to be emotionally depressing. But it's just, that's the truth. Okay. So if I stack more of them, it gets easier to hit one. It's more likely that I will hit at least one. So what we like to do is to define, sorry, let me just scroll through all this quickly, a quantity which we call the areal density. So what is areal density? Okay, it's the number of atoms or the number of nuclei per square centimeter. It's how many targets I have presented in front of me. Okay? So if I think of targets as being, I always do this, it's kind of a morbid thing when I talk about reactions. So here I am, I'm about to try and do a reaction. I'm going to throw this piece of chalk. Okay? If I throw this piece of chalk right now, there's a very thin target of students in front of me. I'm sorry, don't worry, you're safe. Okay, if I throw this chalk, I've only got one opportunity to hit. Okay? And you're all approximately the same size. It gets much more likely if I move here because I see a greater thickness. This areal density is really important because it tells me the likelihood of hitting something if I throw something in a straight line. I see more of you going out now in this direction. So if I miss you and miss you, Adrian's going to get hit. Sorry. I got to get good at some point. All right? So it is basically a measurement of thickness. And if we take a look at what it looks like, let's look at this for uranium-235. Remember that the radius of uranium-235 is about 1.2 Fermi times its mass number to the 1/3 power. That's about 7.4 Fermi. And the neutron, right, it has a radius. It's got a radius of about 1.2 Fermi because 1 to the 1/3 power is 1. Yes?
What is a Fermi?
Oh, thank you. What is a Fermi? Other than a small and very smart dead nuclear physicist. 10 to the minus 15 meters. It's a nice, or you can call it a femtometer, is another one. It's kind of neat. I think, is he the only person who got basically a dimension size named after him? There was no micron. Oh, angstrom. Angstrom got one. Okay. Should be pronounced angstrom, by the way, the A with the O word. But that's the size of the nucleus, angstrom. Okay? So areal density is basically a measurement of thickness. So let's say I'm trying to throw a neutron, okay, at a nucleus with a size with 235 nucleons in it. The nucleus presents a target that's got a radius of 7.4 Fermi, so it's pi times 7.4 squared. That's its area. Obviously, if I have a bigger target, a bigger projectile, it gets easier to hit it too. If I was trying to throw a beach ball, it would be a lot easier to hit people than if I'm throwing a piece of chalk. But the neutron is only about 1.2 Fermi across. The density of matter is about 19.6 grams per cubic centimeter. That's matter where I've separated out the uranium, not by a Fermi, but by about 10 to the minus 10 meters. Okay, an angstrom. Okay. Now we do get one little bit, this is pretty hard. So the dots are separated that you're aiming at by 10 to the minus 10. Okay, but they are 10 to the minus 15 in size. I can't draw that over here. It would just look like a bright screen. You couldn't see something that small. Take that screen divided by 100,000. You're not going to be able to see the dot that I would draw. It's really hard to hit this. So, how good a target is this? What is your probability of hitting it? So, we get one little bit of help here. We don't actually have to have the nuclei hit. The neutron doesn't have to actually hit. Remember I said this, that the range of the nuclear force is about 5 Fermi. Okay? So I've got my uranium, it's 7.4 Fermi across. Okay? I can go out 5 Fermi from that for a total of about 12.4 Fermi. And anything within that area will feel a nuclear force. I just have to get that close and it's a hit of some sort. And I also get to add a little bit for the neutron. The neutron is not infinitely small, okay? 1.2 Fermi. So the total radius that I have is about 13.6 Fermi. So every single target presents, every nucleus presents a 13.6 Fermi radius target. I should square that number and then multiply by pi. That would give me the size that I need, okay? That's the area. That's the target that I'm shooting at. So if you do that, and my math is right, and Sammy is not talking on this, You get about 581 square Fermi, okay? So if you look at that in terms of square centimeters, which would make more sense, I'm approximating 5.81 is 6, okay? It's about 6 times 10 to the minus 24 centimeters squared. That's the size of the target that a nucleus presents. It's that big. And that then creates a neat unit, which we'll get to in a moment. Okay. That neat unit is the cross section, or it's really just the cross-sectional area of the target that you present. That's all it is. Okay? We, instead of saying cross-sectional area, cross-sectional area, cross-section all the time, we abbreviate it as just cross-section. We say the cross-section for a nuclear reaction. Again, it's determined by the size of the thing you're throwing, the size of the thing that you're throwing at, and 5 feet further. That's it. That's pretty much the size of the nuclear force for everything you do in this class, and actually almost everything you do in applications. The 530 number's about right, and that's it. Okay? This is, again, how good a target you have. And Enrico Fermi, noticing how big this is the biggest it gets in the nuclear world. Helped to give it the name that it has today, which is a barn. Okay? A barn, meaning like the broad side of a barn. This is as big as you're ever going to get. Some nuclei will be smaller than others, but I just went to one of the biggest nuclei that you find in the everyday world, which is uranium-235, okay? And the total cross-section for interaction with a proton or a neutron, right, it's about 1.2 Fermi across, is just about 6 of these guys, 6 barns, 1 times 10 to the minus 24 centimeters squared. That's how good a target it is. So if I throw something randomly at a nucleus that's about 1 centimeter squared in size, I have almost no chance of hitting it. I'm going to miss. Unless I stack many of them, wide and deep, then I have a chance of hitting. Okay? This was the idea of the quote about it's easy to hit as the broad side of a barn. Okay? It really is that. Okay? So just to give you an idea, for uranium, this is what the areal density is in terms of atoms or nuclei, because every atom has a nucleus, per centimeter squared. You know, 1 centimeter thick slab, I call that a slab. It's a bit thicker than my iPhone. Okay? That is a slab of material. If I have a 1 centimeter thick piece of uranium here, then the number of atoms per centimeter squared that you would see, if you could actually see the row after row after row of atoms lined up in that thing, you would see that there were 5 times 10 to the 22 atoms per centimeter squared. Each one of them has an area of somewhere between, it depends on the material that you're at, 2 and 6 times 10 to the minus 24 centimeters squared. Okay? That's the cross-section for a single nucleus. But I have more than one. And now you see that this is actually sort of a nice combination, right? This is a very small number. The size of each individual nucleus is quite small. But if I get like a centimeter, that's kind of a unit we can wrap our hands around. It's like the thickness of this chalk. A slab of matter about a centimeter thick, it has a density of atoms or nuclei that's not exactly, it's almost the reciprocal of this. Okay, so it is as big a number as the size of the nucleus is small. So what does that mean? When I get to thicknesses of normal matter that are about 1 centimeter, 2 centimeters, 3 centimeters, I start to get actually a decent chance of hitting something. I will not miss every single nucleus in every single layer. I actually start getting a reasonable chance of hitting. That chance of hitting is the product of the areal density and the cross-section. And typically speaking, for most matter, at about 1 centimeter slab thickness, or 1 inch, depending on the matter you have, how you choose with it, it's about 5%. Still pretty amazing. Just to be clear, what did I just say? I said that like if I have a slab on my iPhone, I ask you to throw something at this and hit it. Okay? You're gonna miss most of the time. Whatever you throw is gonna go right through it and leave. 19 out of 20 times, because that's what 95% would be. But if I made this thing 20 times as thick, 20 centimeters, all right, now you've got a decent chance. Now you're probably going to hit. If I make it really thick, like a meter thick, you probably won't get all the way through it. You'll get some distance in, and then you'll scatter and done something different. Right? So for a 1 meter slab, that's about 500%. Okay? So are you with me up to this point? Please ask questions, take your time. This is really important. I've got you talking nuclear physics now. Yes?
What's the difference between areal density and cross section?
The cross section is the size of an individual nucleus. Areal density is a measurement of how thick a target made of many nuclei is. It's a measurement basically of target. Really what it is it's the density of the target times the thickness. Density is something per centimeter cubed. You multiply it by thickness, and that's something per centimeter squared. But it's how dense a layer of rows of targets I've got. So I've got 5 times 10 to the 22 atoms in every square centimeter. But each one of them is only between 2 and 6 times 10 to the minus 24 centimeters in size. So in other words, if you were looking through this, you'd only get your light blocked about 5% of the time. 95% of the time it's empty. But if I make the slab thinner, now it's not the case any longer. Because if I take the same density of uranium, which is 19.6 grams per cubic centimeter, and I multiply it now by 100 centimeters, now I start getting to the point that it's very unlikely that a nucleus entering the 1 meter slab will make it through the other side and not do something. But do what? I haven't said anything yet about what it will do. It just won't miss. Basically, most of nuclear reactions goes back to that rule number 1. Rule number 1, nuclei are small. So do you understand? It's the number of atoms per centimeter squared in a sample, in a target, in something that I'm trying to hit. Okay, good question. Thank you. Yes.
So you're saying, which cross section are you referring to here? Like kind of skipping ahead a little bit here. But
This cross section is, it's fair. What do you think would be a good name for it? This is the cross section to hit.
we're not talking about cross section for absorption. Kind of
This is just, what would you call this? What kind of a cross section is this? I mean, it's a whole cross section, right? It's not a part of it. It's not the chance to hit the left half or the chance to hit a pie-sized slice in the lower right-hand corner. It's the whole cross section, which we call the total cross section. It is the total probability of hitting the nucleus in some way. I don't tell you what's going to happen next, but it's the chance that you hit it. The next level is figure out what happens. Okay, good question. So, the reaction rate for a target with a given thickness, that's the number of layers that I have going back here. The reaction rate for a target with a given thickness, being hit by a beam with a given number of particles per second, okay, can be defined by a few quantities here. I've got the thickness of the target, which I'm calling R, just because I'm being contrary, maybe I should call it T here, okay? And I have some current of particles that I'm throwing at this. In other words, a number of particles per second. I'm pitching a certain number of balls at this target, okay? And it turns out that you can then write it out really simply. The rate of reactions are simply equal to the density of atoms in here. That's atoms per, or nuclei per centimeter cubed, times the thickness, Again, this quantity now that I have in these parentheses, this has got units of atoms per centimeter squared. This is an areal density. Times how many particles per second I'm throwing at these targets, and how big each target is. That's all this is. This equation is sort of the fundamental thing in nuclear physics when you talk about reactions. The number of reactions that you get per second is proportional to how many atoms you have per centimeter squared in your target, how thick your target is. It's also proportional to how many particles per second you throw at the target. And lastly, it's proportional to this other thing, which is the size of each nucleus, the total cross-section. This is just the reaction rate. Again, I'm not telling you what happens. The particle could bounce off, it could get absorbed, it could cause fission, it could do anything. This is just a chance to hit it. Okay? Now I want you to note that this is valid only when very little of the beam reacts and everything moves in straight lines. Okay? It'd be hard to define a current. A current is sort of the number of particles per second going past some point. That means you're moving perpendicular at that point. It'd be hard to do this if this were disorganized. So weapons don't, generally speaking, have stuff like this going on. Okay? You don't have straight lines. These are the sorts of experiments that we run in accelerator labs. Okay. Also, once the target starts getting thick, and weapons do get thick, that's the whole idea about a weapon, is that they do get, yes?
So just to get like a P target is the nucleus itself and the R target is.
So yes, the P target is the Greek letter rho. It means density. Yes. I'm sorry. Thank you. That's extra points. Point that out when I throw Greek in. That's not fair. The course is taught in English. Okay. This is a sigma, by the way. Okay. The little thing with the hat on it that we use for cross section. Thank you. That's worth a lot. Okay. This is density times thickness. I should have used a D. It's just that all the time physicists talk about rho r. Okay. Rho r is areal density. And the sigma is the cross section. Other questions? Okay. So,
Wait, I think I have a question right now.
oh, I'm sorry.
Yeah,
Yes.
so is the rho the areal density or the density times the thickness?
The rho is just the density. Rho is just, rho has got units of mass per centimeter cubed or distance cubed. Rho r, which I've associated inside of this set of parentheses, that's an areal density. It's the number of atoms per cubic centimeter times the thickness in centimeters. So it's the number of atoms per square centimeter. Let me go back to this analogy here. There's some number, say 20 people here in front of me. And there's some volume that you folks take up over here. And I can define a density, which is the total number of you per unit volume in some roughly rectangular prism in front of me. Okay, that's your density. But that's not what matters if I'm trying to throw chalk and hit you. It's actually like the density of you, the area that you present to me when I throw in a given direction. That's what matters. So it's your density, okay, divided times the thickness that we have. Okay, so there's 20 people here. It's, I don't know, 5 meters by 2 meters across by 20 meters long. 5 by 2 is 10 by 200. So it's 20 humans in 200 cubic meters. Okay, that's not what matters. It's not that there are 200 humans per cubic meter in front of me. It's how many there is per square centimeter, which is how I aim things. So rho times r is areal density. It's really good that you folks are slowing down on this. This is an important piece. Everything else is easy. This is the part that gets a little tricky. So understand what we have here. And we say this in math all the time, that quantities are proportional to one another. This is the number of reactions that I have per second. You can think of it as the number of times I hit per second. The number of times I hit per second is proportional to how good a target, how many targets I have in front of me, how many particles I'm throwing per second, and how big each target is. That's all this equation says. You wouldn't expect it to be proportional to anything else, and you wouldn't expect it to be proportional to anything less. Obviously, if I make each individual target bigger or smaller, the reaction rate should change. Obviously, if I make the thickness bigger, the reaction rate should change. And actually, in a weapon, we make the density higher. The folks who design primaries, it used to be in what used to be called B division in metal war. B division, they call themselves the metal pushers. They actually push metal to higher densities. Does that sound easy? It isn't. Okay, you need a lot of high explosives to get metal to push. So they do that to get the rho R up. That's what they do. And as you can imagine, metal has a tendency to want to go back to its normal density. So you better get everything done quickly. Okay. So I thought about how to present this next bit. This equation, I think, should make sense if you understand each term. It's my chances, my rate of hitting. Now the problem is, if I start throwing things through a truly thick target, if I start by throwing, this was really thick, and I threw 100 particles at the front end, and I start throwing them out, okay? Am I going to get all 100 out the other end in a straight line? If it's really thick. Will I? What will happen? It'll hit something. Yeah, we haven't said what will happen yet. It'll bounce off, it'll, I don't know, you're screaming. Something will happen. You won't get everything out the other side. And so when we start dealing with targets where their areal density is getting big compared to 1 over the size of each target, big with respect to a bar. When the areal density starts becoming of order 10 to the 24, then it doesn't make sense to be using this equation any longer for the whole slab, okay? Because I'm going to use up my beam. My beam's going to actually get depleted as it moves forward. The more it moves forward, the more it gets depleted. So this is a bit of mathematics that I can't avoid, but we don't need to derive, okay? There's a function that represents quantities that vary as their rate of change. Okay, it's called E, or Euler's number. Okay, and it reflects the fact that if I start off with a large number, my I beam on this side, and I start sending things through one after another, my chances of getting all of them out are small, right? You're going to end up somewhere, and there will be a little bit that gets through. In this example, I start off with 5, and I end up with 1. It turns out that that transmission probability depends, again, on how big each target is, how thick you have, and the density. But now it goes inside of this E function. Now the good news is, you all have calculators called phones that have this E function in them. Okay? And what it represents is that as you move through it, the number of particles actually is decreasing. The number that you start with is decreasing. Okay? So basically, what this means is if I need to stop all radiation, let's say I throw a wave of radiation at you folks, and I want to stop it. I'm going to need a thickness such that when I put that thickness up here in this argument, and I look at what gets out, this e to the minus number, that number should be very small. You could think of it, another way that this is sometimes written isn't in terms of e, it's just in terms of halves. What thickness do I need to get rid of half of the particles, or half of the radiation coming in? If I have that thickness, let's say I have a special kind of radiation, and 1 meter gets rid of half. Well, how much would make it through 2 meters? If 1 meter gets rid of half, how much would make it through 2 meters? A quarter. It would be reasonable to say none, but that's not the way it works. The probability is multiplicative. It's kind of like if I have a 50-50 chance of this cell phone landing heads up or heads down, what is the chance of getting 2 heads in a row? And it's going to be a quarter. Okay? That's what this equation represents. I'm not really sure if you're going to need this, but I think it's good that we have it here presented once. Okay? So, once a collision occurs, we get on to the next question. Okay? What happens? I've got a collision. Okay? Well, there are many options about what can happen. One possibility is that what I just threw in bounces off. Okay? One possibility is it just bounces right back off again. All right? That's actually the most likely thing. Almost always, it's the most likely thing to happen. This is not very interesting. However, it is what happens. And we call this, and then of course the nucleus recoils slightly. It is heavy. This was a neutron. We call this elastic scattering. There is a physics reason that distinguishes this from what's going to come next. But elastic scattering basically means two things bounce off one another. There is no energy lost. When that particle bounced off, it lost some of its energy, but it gave it a recoiling heavy nucleus. Okay? That's elastic scattering. It's the most likely thing to happen. The next most likely thing is that the particle does bounce off, but it actually leaves some energy behind in the nucleus. The nucleus is left in an excited state. Okay? And that's possible because if you remember, when I showed that example in the last lecture about carbon-12, nuclei have internal excited states. I described it as being like a chord on a guitar that you can hit. So if I throw something at it, the nucleus could be left ringing, okay, with some of it. Now that some of that energy went into the nucleus, which means that the particle will recoil out, it'll recoil more slowly, and we call that inelastic scattering. That's another option. Yet another option is that the neutron, in this case I'm looking at a neutron, just gets absorbed and the whole thing recoils back. It doesn't have to bounce off at all. It could get stuck. Okay? And that is called capture. Okay? For most nuclei, this is the end of the story. You either bounce off and leave energy behind, or you get captured. Get to higher energy, you might knock a couple of particles out. You might knock more than a couple of particles out. Okay? But for most, this is it. However, for the nuclei that we are interested in for this course, there's another option, fission. Okay? You can capture that neutron and then form an unstable nucleus, in this case U-236, and then fission. But I'd like to point this out, at most energies, when you throw a neutron at uranium-235, it mostly just bounces off. So if you want to make a reactor work or you want to make a bomb go off, you need to throw a lot of neutrons, a lot of times, at a lot of nuclei. And you've got to keep them all packed in so that you don't just miss. Because the most likely thing, again, is to miss. So you have to keep things dense, you have to keep them tightly bound together and throw neutrons at the problems over and over and over and over and over again. Okay, and hope that they don't leak out. You need to make them thick enough so that the chances of them getting out is low. This is an unnatural act. You have to push matter together into one place and just keep it packed into that one place for a long period of time. That's how a weapon works. It's also how a reactor works. But in a reactor, remember in the end, it's the areal density that matters, right? It's the reaction rate is proportional to the density times the thickness R. In a weapon, we drive the density way up. In a reactor, we just make it bigger and bigger and bigger. Okay. Make it big enough and it will, the chances of getting out are very low, and your chances of getting a fission event occur are quite high. So I just need to, I need to make one or the other big. Okay. Or I can try to compromise the two. Okay. So, other big things to note here, energy conservation. There's one other thing to keep in mind with any reaction. Remember we talked about the Q value, which was the difference in the mass between what you put in and what you get out. If the mass goes down, then you've got some energy, right? Yeah, that still holds. You can't do one of these reactions if it doesn't conserve energy. So I have to, the total of the kinetic energy of the projectile coming in, the kinetic energy of the other projectile coming in, or the ejectile, whatever you want to say, the target, plus the Q value, that has to be greater than 0. So here's a little bit of a weirdness. Up to this point, right, I've given you two things. You've got the cross-section, that's your chance of hitting, right? How big the target is. And then I said there are any of these options of what can happen next, okay? So you'd think that if I was a reasonable person, I would just present each of these individual options as percentages, for example, okay? Like I could say that elastic scattering is 50% of the outcomes at a given incident neutron energy, okay? But we don't do that in nuclear physics. We go on and we take that percentage and we multiply it by the total cross-section. And then I say something like the cross-section for elastic scattering, okay? So in other words, I give that quantity the units of cross-section. So you could look at it this way, and this is an actual value taken at a particular energy, okay? For uranium-235, I throw a neutron at it, okay? And I think I did actually do this at thermal energies, the energy of this room, okay? No, it can't be. No, I think I chose 5 MEVs, because there's 5 fingers on here, okay? 45% of the time you'll elastically scatter, 25% of the time you'll inelastically scatter, 10% of the time you'll capture, and 20% of the time you will fission. Okay? It would be great if I just left it at that, but I won't. What I will do is I will take the cross-section and multiply it out. So 45% of the total cross-section ends up being 0.9045 barns. Okay? And it's 0.5025 for inelastic, 0.201 for capture, and I think this is actually weapons minimal. It's like 10, 15 kilovolts. And then fission is 402 millibarns, thousandths of a barn. Okay? So you get it. What I'm doing, you really could think of it this way. The nucleus presents a spherical target to you. It's like I'm imagining that if you hit the nucleus on the right-hand side, you'll elastically scatter. And if you hit it in the upper left-hand side, you're going to cause a fission. This is not actually what happened. There is no preferred direction in the nucleus. This just represents the probability for hitting times the probability of a given outcome happening. Those outcomes are called exit channels. Okay? So you have to hit the nucleus, and then you could have a fission exit channel, a capture exit channel. Why exit channel? Because it is actually the outcome of a reaction. It's actually left. The reaction was when the particles arrive together. The exit is what happens at the end of this. Okay? Yes.
Which neutron energy are we talking about in these examples?
In this one, I can't remember, I'll look at it. I think I did this example at what's called weapons thermal energies.
So when you started out with like the radius of the nucleus, the interaction of the
Yes.
the radius of the neutron, that interaction radius of the pi
It was much bigger, it was about 6 bars.
Oh, that was 6. Yeah, okay. So but that was specific to a certain neutron energy.
That's correct.
Okay, that's what
Now, It is specific to a certain neutron energy, and we're jumping ahead to number 2, reaction part number 2, which was the thing about neutrons getting bigger and smaller. Okay? So we'll get to that in a moment. Okay? This is at a particular energy. If I sum up all those numbers on the right, I would get the total. Okay? And in fact, this is the point, my next thing. The cross-section for a given exit channel can vary with the energy of the incident particle. So what does that mean? Once a particle starts moving, a neutron is moving above a certain velocity, the cross-section for hitting is pretty constant. It's not exactly constant, but it's pretty constant. But as I increase the speed of the projectile coming in, my probability for fission relative to capture might increase. Or my probability of inelastic scattering relative to elastic scattering might increase. Okay? The individual probabilities can shuffle around. The size of the nucleus is pretty constant. Okay? So what does this really look like? You're going to see a lot of plots like this. Okay? These plots are plots of the cross-section on the y-axis in units of barns versus the incident particle energy in units of MeV. So these curves tell you what we call a partial cross-section for a particular thing to happen. So, and here are the different components. The curve on the top, which I did not label, is the total cross-section. And you see, when I get out here, it's pretty constant. Out here, it's not. Don't worry about that. But I don't feel like I thought about actually lying and just showing the plot of 10 MeV. But you're all going to see this sooner or later. This has a little bit to do with the bit that I'll talk about later about neutrons getting bigger and smaller. Don't worry about that. The important point to note here is that the total cross-section estimate that we had before was actually pretty good. Remember, we had about 6 barns. That's about right. That estimate is about right. Okay. Now, what I did here, I know there's at least one colorblind person, and I'm sorry. In different colors, I labeled what these different reactions are, these different exit channels. You can see if the total is about 6, okay, and so this is 1, 2, 3, about half is elastic. So the most likely thing to happen is it just bounces off. Then there's inelastic. Okay? That is competitive in this low energy region, but it begins to dive off. Here's fission. So if you look at this, if I go all the way out here to 20 MeV, by the way, for obscure reasons, most nuclear data stops at about 20 MeV. I think this is really because we have a total of 20 fingers and toes normally. That's really all it is, but we stopped everything at 20. There is data beyond 20, but nobody cares about it except for like a dozen people who I know. Okay? You can see that here, the cross-section for fission is about 2 barns. The total cross-section is about 6 barns. So what is the probability of fission taking place? If a 20 MeV neutron actually hits, what is the probability of fission occurring? About a third. 2/6. That's correct. And yes, it would be nice if I used that a third, but this in a way is more useful. Because if I take this cross-section, that 2-barn cross-section, and I multiply it by an areal density and by a beam current, I can tell you a rate. Not just the rate for hitting, the rate for fission. Because I've now put that in there. Are you all following me at this point? This is the toughest stuff. Yes?
I was just curious, how precisely do we know these probabilities?
Oh, very good question. How precisely do we know these probabilities? Well, we can't calculate them accurately, although we try. If we start off knowing what values are at some energies or on some nuclei, then our ability to predict them gets better. Generally speaking, what bounds our knowledge of these probabilities are measurements. So the problem is that the nuclear force, we don't actually understand it. And the properties of nuclear matter, we don't completely understand either. And I have to combine these two things together to make a nuclear reaction calculation. This is what I do. It's what a number of my students do. And we don't really have a predictive capability. What we're trying to do now is have at least a predictive capability about our uncertainties. That's very important, actually. And so that's where a lot of the focus is right now. Instead, what people often did is that they would take all of the body of data that we have, that's like people have measured the fission cross-section of U-235 for a very long time. There are lots of data points at particular energies with uncertainties, okay? And they take that and they run the best model calculation, theory-based model calculation that they can. And they tune the inputs to that model until they do the best job of reproducing what we've seen. And then if we have a hole in the data somewhere, we use the model to fill in the hole. Because when you do a calculation, either for the design of a reactor, or for a weapon, or for how gold is formed in neutron star mergers, which just happened this last year, which is really cool. If you do any of those things, you need to have an answer for your simulation to proceed. When people run that calculation, they want to know, does the weapon go off? They don't want to get back a response that says, I don't know, you need to not measure these things. That's not acceptable. So what we do is we evaluate the data and put them in. I show this as a curve like this for simplification. The reality is very tricky, okay? The truth is that there are uncertainties in the fission cross-section. And actually, as I change the value of the fission cross-section, what has to happen to the rest? What happens if I increase the value of the fission cross-section? What has to happen to all the other cross-sections?
Decrease.
They say it out loud. Yes, they decrease. They're covariant. They're actually all linked, because at the end of the day, I can't just make the nucleus bigger, okay? I don't get to make that decision. They are interrelated to one another. That's a great question. That's basically now my life work sort of is working back. There are two curves down here that I have not labeled. And I'll tell you what they are. In addition to these outcomes, I can shoot a neutron in with enough energy that it can exit and still leave enough energy behind for another neutron to come out. That's called N2N. So if I do N2N on uranium-235, what do I end up with? What is the product that I end up with? Uranium-234. This is the cross-section, which you can see peaks at just under a barn at around 11 MeV, for U-235 to be turned into U-234 when being irradiated with 11 MeV neutrons. There's that probability. It's about 1 barn, it's about 1/6, about a 16 2/3% chance of N2N happening. And why is that important? Because if after a weapon goes off, I dig out the ground around it, and I find uranium-234, and I know that I made it, and let's say that what I brought in was pure uranium-235, but let's say it was, okay? I know that all the U-234 that I had there came from when the weapon went off. And remember that the reaction rate is proportional to a cross-section times a thickness times a current. If I know that cross-section, then I can use this information to determine the areal density and the current of neutrons that I had in the weapon when it was going off. So I can use that information. So if this curve here is N2N, what do you think this curve is? It starts later. Yeah? 3N and 3N. See, it never gets quite as big as N2N. So then I would see U-233 in the debris. And I use this information. By the way, this little I don't know if you can even see this over there. There's a little purple line right over here. That's N gamma. That's the neutron being captured, which would make U-236. A lot of the game in nuclear forensics is looking at these various products and trying to figure out what rho R and I were when the bomb went off. It also depends on what the material was that you had coming in initially. Was there any U-236 present initially, or any U-234? Okay. This is the hardest stuff that you've had. It all goes downhill and gets easy from here, but it's weird a little bit first. Okay. Now we're going to go to rule number 2. As neutrons slow down, their chances of hitting the nucleus increases. Okay? So you can just take it by my word if you prefer, or you can try to follow this sort of a picture of notionally what's happening. So in the small world in which nuclei exist, things are a bit fuzzy. Okay? So really what happens is I've got this neutron, and it's not like it's a hard ball with a definite radius. It's mostly in one place, it's less in another place, and it's really very less in another place. Okay? If it's moving fast, though, this picture that I had of a ball hitting a nucleus is correct. You could use this. However, if it's moving slowly, then it basically gets bigger. And yes, it does get less dense. That's true. It just gets bigger, and what happens when something gets bigger? Is it easier or harder for it to hit something else? Easier. Okay, that's what happens. So, wow, I misspelled de Broglie's first name. You should have thought that. It's not Louis de Broglie. Okay, it's not even de Broglie. It's actually, I've heard that it's de Broglie. That actually, as you want to sound sophisticated and say de Broglie, but apparently, it's better to be. It's Louis Broglie. Okay, he was one of the original progenitors of quantum mechanics, and he wrote out a rule about the size of particles. And what he said is that the size of a particle is equal to this number h, which is a very small number. It's called Planck's constant. These buddies with a guy named Planck. Actually, I don't know if they like each other. Planck's constant like 6 10 to the minus 34, right? Around 6 10 to the minus 34 joule seconds. Okay, that's h. Okay. It's just a number, don't worry about it. Divided by something we call the momentum of the particle, which is its mass times its velocity. Or you could think of this as being related to its energy. H over the square root of 2 times its energy times its mass is basically the size of the neutron coming in. Okay. So the big thing to note here is that if the velocity goes to 0, as the velocity goes to 0, the neutron becomes infinitely large. Okay? It's a very strange thing. Don't worry, velocity never goes to 0. Okay? So there's no infinities here. Because as the neutron slows down more and more and more, it becomes so fuzzy that some piece of it will wind up near some nucleus somewhere. And it will get captured. It'll interact with that thing. Okay? You see this if you look at cross-section plots. Now, on the cross-section plot that I showed you before, I want you to note that I plotted cross-section in a linear scale versus energy in a linear scale. Raise your hand if you're not comfortable with the concept of a logarithm. Okay? It's a little bit of a weird thing. I'm assuming that some people are still not comfortable, but they don't want to admit it, and that's okay. This is a plot of the cross-section versus the incident energy in what's called a logarithmic scale. What that means is that when I go from one tip mark to the next, the value goes up by a factor of 10. So this is 1 barn, this is 10 barns, this is 100 barns. It's really nice to plot things this way if they're changing over a wide range. If not, I'd have to draw a really long picture. Okay? The way you can think about it is it's kind of like if you're looking up at a tall building. So you know how the very top of the building, as you go further away, the distance between adjacent floors appears to get smaller, right? This is the same thing. As you look up here, the same fixed distance, it appears to get smaller, but it's actually larger. 10, 100, 1,000, 10,000. Same thing happens here in energy. So in this room right now, the particles that make up the air in this room are moving with an energy, it's a distribution of energies, but it's roughly distributed around 25 thousandths of an electron volt, okay? So MeV is 10 to the 6, so this is 10 to the minus 6. That is 1 eV. That is 100 thousandths of an eV. That is 10 thousandths of an eV. And so we're right around here. The air molecules here, or the neutrons in a room temperature reactor, have about that velocity. Okay. What I'm just going to do here is I'm going to highlight the NF cross-section. This is the cross-section for fission. Now you know, way out here where we were looking before, things were very constant. They're not constant here, because the neutron is getting bigger and bigger and bigger. Okay? It's going to infinity, if I was to go all the way down. But keeping in mind that in general, the world doesn't get much cooler than it is here, and perhaps climate change will get even less. You really are sort of restricted again to this point, right? You send the minus, that's 1 eV, 100, and right around here. So at these speeds up here, the neutron is a lot smaller than the nucleus, and all that matters is the size of the nucleus, and that's why this is pretty constant up here. But when you get down here to these low energies, the neutron is a lot bigger, and so your chances of hitting are a lot bigger. And in the case of U-235, if you hit, you're going to fission. In this particular case, at these speeds, there really is nothing competitive to fission. This purple curve, the only one you can see, that's neutron capture. And if you look again, and right around here, it's down by, I don't know, maybe even 2 orders of magnitude. In other words, it's 1%. If you hit at these energies, you have a 99% chance of fissioning. If you go up here, it's not quite so clear any longer. Okay? If you go up to these higher energies, fission actually becomes a minority. This is the fission curve right here. Here's the elastic scattering. Okay? So if you want the neutron to induce fission, you want to slow it down. That's how you make it induce fission. It's all about slowing it down in U-235. Okay? And again, here's room temperature, just to show you where it is. Okay? At 300 Kelvin. Reactors are a bit higher than this, but not much. The surface of the sun is at about a volt. Okay, so that's right there. It's still quite low in energy. Okay, 1 eV. So if you look here at room temperature, this cross section isn't quite 1,000. I think it's actually 584 bars. Okay, I just remembered that off the top of my head. I could be wrong about that. Okay, that's really weird. Remember we figured out that the nucleus is about 6 bars. That's the size of the target. So I don't really like to say that uranium-235, in a way it's unfair to say uranium-235 fission. I have to say it's uranium-235 neutron-induced fission at 300 degrees Kelvin, which is room temperature, has a cross-section of 584 bars. Really what I'm telling you is that down at these low velocities that thermal motion represents, the neutron is really big. And now it starts getting easy to hit. And if you hit, you induce fission. Okay? This is in U-235. So what does this look like for U-238? Remember that most of uranium is U-238. Here's the same set of curves, and I've made fission clear on this curve, okay? If I go up to high energies, fission probabilities in U-235 and U-238 aren't all that different. But at low energies, it doesn't really happen. There's room temperature, and the cross-section for that, the value that I would read off is it's less than 10 to the minus 4, but more than 10 to the minus 5 volumes, okay? What will happen at those energies? Okay, the nucleus is still a certain size. It turns out, like the biggest curve here, I'm trying to look at this, it looks like the single biggest curve is the green, which I think is elastic. Is that right? Yeah. Okay. The single biggest curve is elastic. The most likely thing to happen at that energy, if you're a neutron, is to bounce off of uranium-238. U-235, you're going to cause a fission. U-238, you're just going to bounce off. Okay, and you'll lose a little bit of energy, but not very much. Okay. So finally, let's look at plutonium-239. The one other thing that matters for us really in our weapons world. Okay, there's the value at room temperature, and it's almost a full 1,000 bars. Actually, that's a bit of a problem in the weapons world. It means that if I slow down neutrons in the presence of plutonium, it's even more likely to induce fission. And part of what's involved in making the weapon work is to make sure that things happen when you want them to happen and not earlier. So there's a whole issue with plutonium with what's called pre-initiation that basically amounts to the fact that the cross-section for uranium is a bit more than half a kilobarn, and for plutonium it's a full kilobarn. That makes plutonium a much harder material to work into your weapon. Get it close, and it'll go over the line, even at room temperature, into fission. So this is a lot. It's a lot to ruminate over. All these slides will be out there. Okay, take your time. We're actually almost done here. We're on the last leg of reactions. I want to. Okay, let's see if I'll go a little bit into this. I think we're almost done, and Carl will finish this up with them. 3 rules about nuclear reactions. Okay, the last one is fusion. Fusion reactions require high energies, since the reactants have to overcome electrical repulsion. Okay. I guess before I go on, let me just take a break. Does anybody have questions about this? It is kind of weird. You need to be comfortable looking at plots like this. You don't need to be able to necessarily draw them all. Okay. And there's a lot of you who have not asked about the big ugly thing in the middle. I appreciate that. That's the stuff I'm really interested in, but we're not going to talk about that in this class. We don't have to. Okay. I think that these are called resonances. They're really neat, but you don't need to worry about them. Okay. You do need to be able to say, if you see a plot like this, and I say, tell me what the cross section is for, elastic scattering on plutonium-239 at 1 eV. You need to know, well, 1 eV is 10 to the minus 6 MeV. This is 10 minus 5, so here's 10 to the minus 6. You need to walk up until you find the elastic scattering cross-section. You look across and say the answer is 10 bars. Once you have that, you go plug it into that equation. You don't need to look anymore. It's a table. That's all you really have to be comfortable with on this thing. Okay? All right, fusion. Fission releases electromagnetic energy. And I've already gone through this before, and I didn't even correct my title before. In contrast, fusion releases nuclear energy. The main reaction that we've used for a long time in nuclear weapons is deuteron on triton. Okay? This reaction goes on only if the deuteron and triton can get to within that 5 Fermi magic distance. Okay? And then you shoot out with a 14 MeV neutron and a 3.5 MeV helium-4 nucleus, which we call an alpha particle. Now, and again, if you look at the sizes here, this helium is about 1.33 Fermi, this is about 1.2 Fermi. So really, the D and T are small enough to have all of their nucleons within the range. of the strong nuclear force. And why is that important? Because when I start down here, here's deuterons and tritons. This is the binding energy for nuclei. I start out down here. If I fuse, I end up at helium. Fission takes me from here to here. That's the gain in binding energy for nuclei. Fusion takes me from here all the way up to the helium 4p. So you need to remember when I showed you this is the binding energy per nucleon, not the total binding energy. Uranium has 235 nucleons plus one for the neutron that came in. DT has 5. But if you look at the energy released per nucleon, fusion beats fission. This gives you 17.6 MeV. This gives you 200 MeV. But this is 17.6 per 5 mass units, as opposed to 200 per 236 mass units. Okay. So pound for pound, this is a much more plentiful source of energy, fusion. Okay. But you need to keep the system up high enough in order to overcome that electrical repulsion. Okay? If I make a plot of the cross-section, it now does exactly opposite to what the neutrons did. And remember, the neutrons, when I slowed them down, they got bigger. It was easier to hit. Now, if I slow it down, I don't even get close enough for the nuclear force to kick in. They just miss. They deflect one another. Like the same, like north poles and north poles on magnets. They just bounce right off of one another. Okay? And it's a really, really, really sharp rise. And I can even identify how much energy they need to have in order to get to the point that these things are touching, which isn't quite needed. Again, you need to go to about 5 Fermi. And it's about, in the case of deuterium on tritium, I can calculate this out, and it's about 444 keV. So if I was to turn that number into a temperature, because things are bouncing around, okay, is to turn that into a temperature. 1 billion degrees is 86 kilovolts. So roughly speaking, this is like 5-6 billion degrees. Okay. Weapons don't get that hot. They don't even get close to that hot. The sun doesn't get that hot. Big stars don't get that hot, except maybe once at the very end of their life. Okay? That is a huge temperature. So that means that the fusion reactions that go on in a weapon shouldn't be going on. That's the temperature in a kind of typical of a weapon, 5 to 10 kilovolts. Why does it work? This will be my last thing I show today. So this is another weird aspect of the quantum world, and it's an effect called tunneling. I can't lie to you, but I can show a pretty graphic, which I found on the web, and it sort of describes it to you. You know, classical physics, you have to climb up the hill, get to the top, that requires energy. In the quantum world, you can tunnel. I can start with a particle on one side, and as it moves through the barrier, classically, it just wouldn't make it. It doesn't have enough, note the height of this particle, it doesn't have enough energy to be able to get over it, okay? But with tunneling, it means that there is a small possibility of the particle making it all the way through. It's extremely small. So you need a lot of collisions for this to go on. But fortunately, hot systems have things moving around very fast, and that they have a high likelihood of running into one another. So I'm going to stop. I actually only have 3 slides left, so there's very little left for Carl. I'm going to have Carl come back here, though, and start again, just at this point again, really quickly. It's only two additional slides, okay? And finish up fusion reactions with you on Monday. And I think that will give Professor Knopf more time to be able to lecture and catch back up again. And then when I come back on Wednesday, from where we'll be discussing these cross sections and how accurate they are, I'll be able to talk a bit more about reactors, which are really just very, 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 very slow bodies.
If you came in late and didn't give me your homework, please bring it to me.